invited with us Claudio Maccone. Hi, Claudio. How are you? You are mute.
Sure. Thank you. I am fine. Thanks.
So where are you located, Claudio?
Okay, I am located in Italy, and in particular in the town of Turin, Torino in Italian, which is in the north, in between Milan and the French frontier.
Thank you for being here to talk to us about your new book. And I remind our viewers that they can tell us where they are watching us. We want to hear about you. We want to know where you are from, and don't worry, you will also be able to ask for questions in a few minutes. So I invited Claudio because he has a new book which has been released and titled, let me call the title. The title is Evo-SETI, right?
Yeah.
But before talking about the book, I'm very curious to know, Claudio, your motivation for this research that you are doing. I mean, you are an Italian astronomer, a space scientist, mathematician. I should mention that in 2002, you were awarded the Giordano Bruno Award, which is kind of a very cool award, by the way. Congratulations.
Thank you.
And since 2012, you're the chair of the SETI Permanent Committee of the International Academy of Astronautics. So yes, you're involved in SETI, but tell me a bit more about yourself and how you came into this idea of creating a new model, a mathematical model to understand the evolution of life.
Wow, thank you for asking me. Actually, not many people ask me this exactly the same question. So anyway, let me tell you, many years ago, I think in 1985, I came for the first time to know about SETI, and that was when I read the book Contact, written by Carl Sagan about Jill Tarter and what she was doing and the SETI searches that the SETI Institute under her direction and Franck direction were doing. So before that date, I have to confess that I didn't even know what SETI was. But when I came to read that, I was so charmed that I decided to take a closer look. And so I wrote a message, you know, at the time there wasn't internet yet. It seems funny for today's situation, but that was the situation. So I wrote a paper letter, actually to one person, Kent Callers, who you may have seen the movie Contact, and the Kent in the movie Contact was inspired exactly by this person, this true person, Kent Callers. And he was working with Jill and other people at NASA Ames on SETI searches. So I wrote a letter to him, say, sir, you know, I came to know about you, and if you would like to let me come to the NASA Ames and give a talk, I would be glad to do so. And incidentally, that was my first visit ever to California. So it was very nice, not just for SETI, but also for the scenery. Okay, so this is what happened. I went there and they gave a talk, but let me say a few words about this talk. Basically, I was talking about the KLT, standing for Karhunen-Loew transform, which is a mathematical algorithm that I had been working on already for 10 years or more capable than the Fourier transform to get difficult and weak signals out of background noise. So no concern about civilization, no concern about the Drake equation, just you know, detection algorithms, nothing else than that. But of course, difficult in mathematics because this uses the mathematics of quantum physics, so Hilbert space, principal axis transformation, and all that. So I gave the talk, and actually I have to say that only Jill Tarter and Kent Callers, of course, and another person that you may know from Stanford, Ivan Linscott, were the three people that actually appreciated my talk. Unfortunately, I cannot say the same about the boss of the SETI community then, Barney Oliver. Now, Barney was an engineer that had his training during the Second World War. So clearly, you know, sines and cosines were the best for him to to get signals out of noise, and that was it. So I was talking something about for the far future. Now, of course, it has been used by many people around the world, including the SETI Institute. But this is to tell you about the progress that SETI had to undergo in decades, 30 years, even more. Okay, so that was the beginning. And then in the same year, 87, I also had the privilege to go to Hungary. Please remember that at that time, the world was split in two halves. The United States and the Western community, and the Soviet Union and the Eastern community. So the meeting was held in Hungary on Lake Balaton, simply because we, the Western, were allowed to go there, but they, the Soviets and people, were not allowed to come to the West. So we had to go there. And that is where I came to meet all the great people in SETI, starting with Franck and the Russian Nikolai Kardashev, you know, all the important people. And that was really enjoyable, very good. And just to complete the story, later, of course, I met again with Jill, and that was in France at the Nancy radio telescope. Nancy, as you know, you're French, it's about 200 kilometers south of Paris, beautiful radio telescope. Jill was going there with another French astronomer, François Biron, that you may have met. And so that was practical experience on SETI reader. And that's it. After that time, I've been in touch with them for the rest of my life. Thank you.
So that's the way the SETI interest started. Yeah, it's always interesting in science. Sometimes you start this by one small meeting, and then you meet people, and then you travel in different places. And I'm like you, I do remember vividly conferences where I met people with who I'm working still now. And sometimes I remember the sceneries or the country or the context of the country. Like I think taking an airplane to go to a place you have no idea about the language, and you learn and you discover it with those people who become your friends later on. So great.
Yes.
I'm glad I hear this story. Now I know a little bit more about yourself. So we have people joining us from a lot of different places, from Montreal, in Canada, in Europe. We have Switzerland, France. And then we also have people from New York, Pennsylvania, New Jersey, India, and more of them are coming as we speak right now. So let's talk about EvoSETI. That's the way I say it with my French accent. I don't know how you say it with your Italian accent, but let's say that EvoSETI is clear for everybody. So can you tell us a bit more about this model? It's a very complicated model. I just give a warning to people. So there is a book, and maybe you can share a few slides and show us some of what you have prepared to.
Yes, thank you very much. So this is the title slide, and actually the title of the book itself. So EvoSETI stands for evolution, meaning the Darwinian evolution that brought life to Earth, starting about 3.5 billion years ago, and going up to today. And SETI is, you know what SETI is. And the subtitle of the book is Life Evolution Statistics. This is the important word. On Earth and possibly on exoplanets. So this is the title page. And let me now show you, please, the cover page of this book. So this is me, and this is the title, EvoSETI, and this is the subtitle, Life Evolution Statistics on Earth and Exoplanet. And actually the drawing is the center of the Andromeda Galaxy, M31, but they put the Earth at the center because the Earth is the only planet that we know is really hosting life. Mm-hmm. So at the moment, of course, we hope to do better in the future, but at the moment, this is the situation. And just some details. It's a new mathematical book. The cost, I'm really sorry, is rather expensive, but don't blame me, please, because it's the publisher that fixes the costs of the book. And actually, just to be frank, I am getting no more than the 8% out of each copy sold. So it's about $100 and even more for the hardcover book. And this is the beginning of the story. Now, let me ask you, Frank, would you let me please go on to the real important first slide, which is this one? So
maybe you can explain the idea of of the theory. What exactly trying to achieve?
Yes.
What's the question you ask yourself first?
Now, look, the idea of writing this book came to me from attending astrobiology conferences. Astrobiology is a wonderful science that goes beyond astrophysics. So I know that the vast majority of people interested in SETI today have an excellent background in astrophysics. Astrophysics is physics. Astrobiology is more because it's trying to bring life into the picture. So I attended many conferences around, and I have to say that I was a little bit disappointed, let me speak frankly, because SETI is only left on the sidelines of astrobiology conferences. They allow us to give a talk, but you know, they prefer to give the privilege to people training chemistry, paleontology, you know, all related disciplines, but not really much mathematics.
Yeah.
Now, this left me unsatisfied, and especially in regard to the definition of life, because when it comes to say what is life, question mark, they tell you about 10 or 20 different answers, if not more, and each of these answers is tailored to the particular knowledge of the person speaking. So there are people, you know, stressing DNA, RNA, and all that. There are people stressing paleontology, and so on and so forth. Now, let me say that as I am a mathematician, basically trained with a PhD in mathematics, I was not happy about that, because in mathematics you need just one definition. If you have 10 definitions for the same thing, it just becomes a mess. So in my book, EvoSETI, I try to give one precise definition of what life is. And this is a mathematical definition. It is not based on chemistry, it is not based on paleontology, and on sociology. I apologize to these learned people, but you know, I wanted to write an original new book. And it is, as you said, Frank, a highly mathematical book. So
this function here, just to go back to what you're showing on the screen right now, is basically the heart of this. It's a mathematical definition of the evolution of life. Okay, so on the x-axis we have time, on the y-axis we have a probability or density, basically, and maybe you can explain the concept here.
Yes. Well, when you study mathematics, you know, you find infinite curves going from minus infinity to infinity or something like that. Now, this is not the case for life, because we all know that in time, life is limited. You know, all of us and animals and plants, and presumably extraterrestrials as well, have a birth time. I mean, they're born at a certain time. And in my convention, the time axis, small b, is the time of birth, right? Then this little creature grows up like this until it reaches this point. This point, I had to give names. I called adolescence, but actually, I should have been more precise. It is puberty. Mm-hmm. Now, puberty for all animals and plants also is the time when the living creature reaches the capability of producing offsprings. So before this, no offspring, but after that, offsprings can be produced, not necessarily, but they can be produced. So this is, of course, mathematically speaking, the inflection point where the second derivative equals 0. And then life continues and keeps going on for this living creature until sooner or later it reaches a peak, meaning the time when your health is best. You know, you can produce the best works if you are a human, or you can do, I don't know, hunting in the best way if you are an animal and things like that. So the peak is, of course, the point where the first derivative equals 0. And then the decline starts. So after that, you start going down until you reach a point that I called senility. And this is, of course, the descending inflection point. So the puberty is the ascending inflection point, but the senility is the descending inflection point. Now, at this point, the log normal distribution would keep going this way with a long tail, actually an infinite tail, going to touch the axis, the time axis at infinity. But this cannot be done as a model because we do not live for an infinite amount of time. So at this point, I had to change the definition. And the easiest way was to suppose that from that point onwards in time, you just follow a straight line that finally intercepts the time axis. And the point of interception, of course, is death. So this is my mathematical definition of life. No more, no less.
Aye, that's ambitious, but I like it. So in this next slide, you can show that this applies as well. This applies as well for civilizations.
Yes.
So let's show it briefly, the civilization that you have in mind, the first one that came in your book, I think, or in your papers. The next slide.
Thank you. Thank you. Well, look,
what a surprise.
I hope you'll forgive me. I have to apologize, but anyway, let's go ahead. So since I was born in Italy, as you can imagine, when I was a young student, a boy actually, they told me the history of Rome, all the emperors and the wars or whatever, which I didn't like that much, actually, I have to confess. But anyway, I had to learn it. And so the point in the book is that I derived a set of equations that I am not telling you about, such that these curves in red is the history of Rome cast in mathematical terms. Mm-hmm. So on the axis, the horizontal axis, you have all the years as computed in the Christian community. So 0 is the time of the birth of Jesus Christ, of course. And Rome was established according to history books or legends or whatever whatever you like. It started in the year 753 before Christ. So according to this convention, the negative years are before Christ and the positive years are today's years, right? So the starting point B is minus 753. And then for about 300 years, it was practically a very small domain. Mm-hmm. This is called the history of the kings of Rome, and so on and all that. But finally, around the year 300 before Christ, which is the time of the Alexander the Great's empire in Greece and in the Middle East, well, then things started to change. And so the importance of Rome grew up until it reached the inflection point, the ascending inflection point, and that was about after the end of the Punic Wars. You know, there were 3 Punic Wars against Carthage. So at the end of these Punic Wars, that is 146 BC, this is the point. And then the empire kept, and then first republic, but then empire kept expanding until it reached the maximum. And the maximum was reached in the year 117 under Emperor Trajan. And of course, Jesus Christ had been born, and so Christianity started at this point. Mm-hmm. And after that, it goes down. But as I said in the previous story, it cannot go down to infinity as in the solid curve. So at the inflection point, the descending inflection point, you consider the straight line, which is this not dot, but this half line going from the descending point up to the year of the collapse of the Western Roman Empire, which is traditionally the year 476 AD. So the real history of Rome is this thing up to this point, and then the straight line down there. Okay, that is the example.
So you have done that for other civilization. Let's go quickly on each of them, but not each of them, but just show us the table, because I like this table where you list a lot of all those civilizations on Earth. This one.
Thank you. So I just
Let's
consider
not go
some
through all of
important
them,
civilizations.
Claudio, because we're not gonna have much time. But you list Greek, Rome, Renaissance, Italy, the Portuguese Empire, etc. Even use the French and the British Empire and the USA. So let's combine those that you did in your book.
This is it.
Yeah.
So Greece is the red thing. Again, 0 is the birth of Jesus Christ. Violet, purple thing is the Roman Empire. Exactly. Then about 10 centuries that were really lost in technological development to a large extent by the Western civilization. Not completely lost, but you know, the warfare was so big that everybody was at war with anyone else. And so even Carl Sagan said in his book Cosmos, you know, these were 1,000 years lost by the Western civilization. And after that, Italy, Renaissance Italy started again, and these are the centuries of Renaissance Italy, the green curve. And then the colonial empire, you know, Portugal, the brown one, Spain, the orange one, France. France is a bit peculiar because it has two different phases, before the revolution and after the revolution. Anyway, in rough terms, the blue curve is light blue curve is France. Dark blue is Britain, which is higher, as you can see, than all the previous empire. And finally, the red thing is the United States of America.
So one question I have is why the British Empire is higher compared to the other, and then the USA? What is the significance of this?
Very good. Thank you very much. Let me tell you the trick about all these curves that are bilog normals. Well, the trick is that the area under each of them is the same. Yes. And this mathematics is called the normalization condition of the probability distribution. But in practical terms, the area is the same. So since all these areas are the same, for instance, when you come to Britain or the United States, of course, since the two areas are the same, so as to say, the peak is much higher, but also it lasts a smaller time, which proves that evolution is increasing faster and faster.
That's a very important point in your book, in fact.
Thank you.
We see the older civilization have a slow growth compared to the youngest one. And the most recent one, the USA that you show here, has a much faster growth, but its duration is smaller because of that. So that's going to bring us to the good transition, maybe to the information entropy. I think that's the next slide you have, where you describe basically the different level, the difference between civilization in bits.
Yes. Okay, let me please go back a moment and consider, for instance, the difference between the British Empire, the blue thing, and the American Empire, the red thing. Now, of course, we know the peaks of each of them. For Britain, the peak of the British Empire was roughly around 1904, before the First World War. And for America, in my opinion, the peak was when the Americans landed on the moon. So we know the dates. And since we know the dates, we can find the difference in between these two peaks. And so peak of the second one minus peak of the first one multiplied by B, which is this factor here. I cannot tell you how it's basically this B is the velocity of evolution of life over 3.5 billion years, okay?
Yes.
And then you natural log of 2, which is just a normalization constant. And what comes out this is the difference in entropy. Now, I have to be frank about one point when I use the word entropy, because this may be misleading. All of us, when we took physics courses, you know, came to study the second principle of physics, second principle of thermodynamics, you know, telling us that the entropy of the universe is increasing more and more and all that. But that entropy is not the entropy that I used in my book. That entropy, the one about the second principle of thermodynamics, is the entropy of gases. You know, the entropy of Boltzmann and Clausius and also Maxwell. So it's the entropy of the kinetic theory of gases, and it works wonderfully for that things. But here we are talking about different things because we are not a gas. I mean, this is obvious, it's trivial, but not many people have realized the difference between gases and humans, for instance. So I had to use a very different definition of entropy, and this is the information entropy that was introduced by Claude Shannon, an American engineer and mathematician, in the year 1948. And it is completely different from the previous entropy of Clausius, Boltzmann, and Maxwell. It's more complicated. I cannot give you the equation, but it's more difficult.
But it quantifies basically the amount of information into a signal. That's the kind
Exactly. So let me tell you that when I gave this talk at the SETI Institute, I had a message from Nathalie Cabrol that, of course, you know, well, she said, but look, this looks very much like a sort of theory, not only of evolution, but of increasing complexity. And so it is. The complexity is measured by bits, meaning that the more bits made up for the living thing, the more complex the living thing is.
Yeah.
Okay. So I hope I've explained that in easy.
I think you summarize well the concept of this entropy difference. So concretely, do you have a slide where you show some of those values? I've seen some of your talks where you discuss this.
Yes.
The number of bits. Where's the next slide? Yes.
Okay.
Right.
Now,
this
look,
is the one I like.
I
know it's just one line. It's a very important one.
Yeah. Thank you very much, Frank. Well, this is the one I like too. I mean, it's really the best, let me say, discovery that I could reach. So on the horizontal axis, again, we have time as usual. So 0 is over here, and that is today. But the time here is measured in billions of years with the minus sign, of course. So this is half a billion years ago, 1 billion years ago, 1.5 billion years ago, 2 billion years ago, 2.5, 3, and we start conventionally at 3.5 billion years ago. I mean, of course, I know that some paleontologists say that life started on Earth earlier than that, 3.8. Someone even says 4. No problem. For me, it's a child's game to change the number, but the important things are the equations, not the numbers. Now, the great discovery is that the Evo entropy, that is the entropy in the sense of Shannon, as I described, is just a straight line. Look, I couldn't believe that that was true because this is very easy to understand, but also to prove it is not easy at all. And I had to use the NASA symbolic manipulator called Maxima, which was created with NASA funds at the time of the Apollo flights to check the orbits given by the French Charles Delaunay about 100 years earlier. So it's not a trivial thing, but in my book, of course, you can find all the computer codes that I use to that. So conclusion, this is the straight line giving you the Evo entropy of the whole of evolution of life from minus 3.5 billion years ago, when RNA conventionally started, and RNA is the first molecule that can reproduce itself. Mm-hmm. Cells, it's a live molecule, up to now. Good. But then a temptation. What is the temptation? Well, the temptation is to extrapolate that from the past, all this is the past, into the future. So just imagine that you keep going like that in a straight line, and what comes up? Well, I tell you that by words, okay? But in my book, of course, you find all the reasoning and the equation and the codes and whatever. Well, I have a feeling that we are living through a very special time in the evolution. This is called the approach to the singularity. The singularity in the jargon of scientists is the time when computer will take over with respect to us. I am terribly afraid.
Sharing your screen, Claudio, just this way we can.
Sure.
This is interesting, so I want people to pay attention to what you're going to say.
Thank you. So let me say a few words about the singularity. The singularity, by definition, is the time in the future, but not so much in the future, say 20 years, no more than 50, say, or a century. The time when computers will become so intelligent that they will get rid of us. And, you know, when I read about artificial intelligence and the cars that drive alone and the robots that take us by hand and all that, you know, honestly, I feel afraid about that. But if that is the next step in evolution, there is nothing we can do. So, conclusion, the future, that is the extrapolation of the past that I showed you earlier, along the straight line, is actually a world no longer made by humans. It's a world made by computers. And computers already today reproduce themselves by computers technique. They don't have sexual reproduction as we have.
Mm-hmm.
They have computer reproduction. And perhaps this is going to explain the Fermi paradox, meaning that so far we didn't get any signal in the sense that we are looking for, but that could be because those machines are so much more advanced than us. For instance, they could use entanglement or other tricks that we don't know about yet, that, you know, we may have missed the contact because our technology is too childish compared to the very advanced technologies used by computer. Thank you.
All right, thank you. So one of the things that I was thinking when I was reading some part of your articles is that you show in your paper that the difference, you could compute the difference in bits between different type of moments in the civilization, like when the Inca met the European at the time, the difference in bit was, from your calculation, something like 1 or 2 only, something like this, right?
Yes.
And there was a huge difference already in the amount of information from both of these civilizations. But now when you look at your figures that you show, we are reaching a point for which a few years will increase significantly the difference of bit. So it means that when we're going to see a civilization, if one day we meet a civilization, an extraterrestrial civilization, it's very unlikely that we'll be exactly at the same time of evolution of our civilization.
Yes.
If they move by 50 years in one direction or another, we will have basically a difference in bit, in difference of civilization, information in the civilization of 1 or 2. So we'll be as different as when the Inca met the Spanish conquistadors at the time.
Yes.
That's a frightening, that's frightening, no?
It is frightening. Thank you for pointing it out. And it is frightening me, but you know, I just did the mathematics. I couldn't do better than that. Let me please add just one comment about what you described. You know, this idea of the clash in between the Europeans, Cortes and the Spanish, with the Aztecs is instructive because it was not just a battle. The surprise is that about 10,000 Spaniards could subdue in 3 years' time 20 million Aztecs. Now, the historians, of course, they tell you that many people in the Aztec Empire were ready to rebel. All that is true. But I have a different opinion, or a especially important opinion. The point is that the Aztecs had a psychological breakdown. meaning that they realized that the Spaniards were higher level civilizations. And so they could not fight against the Spaniards as they had been fighting against the other people in Central America, you see? And that explains why 20 million Aztecs were subdued in 3 years' time by the Spaniards. And exactly the same story repeated 30 years later in Peru, when Pizarro arrived with the Spaniards and he subdued the whole Incas empire that was even larger than the Aztec empire. So this is precisely what I am afraid about. And let me tell you that this is the #1 reason for writing my book. Now, as you know, I am the chair of the SETI committee. And in case we find the messages or just signs of an alien civilization, my concern would be to find out how much more advanced than us those aliens are. You see, this is the important thing. What is the difference in entropy, Shannon entropy, between them and us? We have to quantify that. Otherwise, we end up like the Aztecs.
So how are you going to do that? Let's assume that we get a signal from ET coming to us with lasers instead of radio.
Yes.
Will you be able to quantify this?
Yes. Now, let me tell you my idea. Actually, I didn't put that into equation because I didn't have the time. I had to publish the book. But let me tell you the nice short story. In the year 1502, Christopher Columbus was exploring the coastline of today's Nicaragua, okay? For the first time, of course. And that was during the 4th voyage of Columbus, after he had been finding the Taínos and other people. So all of a sudden, he noticed that a group of ships were arriving. But they were big ships, not small ships. They were not Spanish, but yet nevertheless, they proved that the civilization that had produced those ships was certainly more advanced than the Taínos and the cannibals and all that only had boats and barges. So just by looking at the ships, he came to realize that nearby there had to be a much more advanced civilization. And we know, of course, that was the Maya civilization. And actually, they were Maya ships that were going around to sell cocoa, to the nearby countries. So they were merchant ships, they were not warships. So that is true history. This is not science fiction. But now let's move the same story to space. Now, I am absolutely sure that sooner or later we will intercept radio communications between alien spaceships. If they go around the galaxy, they have to communicate in some way. So if we can detect communication of different levels in between the ships, we can possibly detect different civilization. And by virtue of my mathematical theory, estimate what is the entropy difference in between this civilization. This is the goal of my book.
Thank you. That's kind of what I was thinking about while I was reading your papers, in fact. So this could be a way, this mathematical model could be a way for us to quantify the difference between us and this extraterrestrial civilization when we connect with them somehow. And,
yes.
And that's really I think the important part of this book. And that's why I wanted to spend some time talking about that before we part, because we are way over time here. But I wanted to say that we have people joining us from other parts of the world, Texas, New Zealand, Germany, and California. So you are welcome. And we have been talking about EvoSETI with Claudio Maccone. Claudio, thank you very much for coming to our SETI Live to talk about these interesting models and to talk about your book. Your book is available, so if people want to know more about the theory and maybe improve it or maybe find some new application about it, I recommend they have a look on the book and connect with you, of course.
Well, thank you very much, Frank. This is one of the best meetings I had, because this was not mathematical, but it really pointed out the importance of the book, innovative aspects of the book for the future of SETI and hopefully discovery of an extraterrestrial civilization. Thank you so much, Frank.
Thank you very much, Claudio. Thank you to all of our viewers. Don't forget, we are the SETI Institute. We are a non-profit organization. So you can follow us on all social media. You can register on to receive our newsletter called Journée, attend to our SETI talks, our SETI live, ring the bell here on YouTube so you know when we are posting a new discussion on another topic related to astrobiology, SETI, the search for life in our universe. And if you're inclined, you can also make a donation, join our SETI Stars program, and be there, help us. We are not going to find life on this large universe without your help. So thank you very much, everybody. And thanks again, Claudio, for this amazing conversation.
Thank you.